Hi everybody. So here's a really fun conversation, which normally we would have had way back at the beginning of the term, but because those first couple of labs, we were trying to do them in an hour and a half and just go through so quickly, we didn't even stop and have this. So I'd like to have this conversation now because I think it's a really important one. So it's about using your meter. And I mean, it's a practical conversation in terms of it tells you how to use your meter, but it's a very theoretical conversation. This lesson is really going back to theory so you can understand what's happening. For starters, we're going to talk about multimeters, measuring your voltage and measuring your current. So we're going to talk about it as a voltmeter. We're going to talk about it as an ammeter. Now, the new ammeters, of course, they're clamp-on, and it cheats, okay? Because we can just clamp on the wire without affecting or interacting with the circuit in any way. Okay, so we're going to take a step back to a more traditional ammeter, which you needed to use your two leads in order to take a current measurement. You actually had to open up the circuit and place your meter in it. Okay, so we're going to look at that. We're going to talk about why that works, how that works, and why the conversation is important. Okay, so let's start with this little piece of understanding, and that is that when we place our meter in or on a circuit to take a measurement, we have to make sure that doing that doesn't change the circuit, right? The circuit that we want to measure has to remain unchanged while we take the measurement. Otherwise, the measurement is useless. Okay, so that's the understanding that we have to walk into this conversation with, is that adding the meter to the circuit must not change the circuit in any significant, substantial way. Okay, so let's build a circuit and then we'll figure out how to take a measurement. I'm going to go back to all of your first level theory. I think we can go way back there with the conversation. We'll just go with a DC power supply and a couple of resistors. So there's our DC power supply. I'm going to place two resistors in here in parallel. Okay, so there they are. All right, now the first thing that we want to identify is the fact that this resistor, R1, has a particular value for resistance. This resistor, R2, has a particular value for resistance. And RT, the total resistance of the circuit, okay, is going to be something less than 1 and 2, right? Because the reciprocal equation is how we calculate RT in a parallel circuit. Okay, we've added an extra bridge over the river. We can get more cars across the river, which means there's going to be a higher current here. Let's put this in here. So we have I1 and I2. There's a particular number of cars getting across this bridge. There's a particular number of cars getting across this bridge. Add them up. That's IT, the total number of cars getting across the river. The only way we accomplish that is by RT being smaller than R1 and R2. No matter how big or small those bridges might be, we get more cars across every time we add another bridge. Right? Okay. So, first thing we're going to do is measure voltage. Now, what do we know about voltage in a parallel circuit? It's constant, right? The voltage drop at each parallel branch is going to be the same as the applied voltage. But the point of the conversation is, how do we use our meter to measure that? We know that, okay? We've done lots of math on it, but how do we measure it? Okay, well, when we measure voltage, we place our voltmeter, we place our two leads on either side of a resistor. So my question is, what is the voltage drop across R2? Okay, I would take my voltmeter and I would put my two leads on either side of that resistor and say, what is the potential difference across that resistor? What is the voltage drop across that resistor? What is the voltage there at the resistor? Say it however you want. It's the same idea. I'm going to draw it differently just so we can appreciate the point of this conversation. What we've done is we have created a third parallel branch in our circuit. All right, by placing the voltmeter, by placing the two leads of the voltmeter on either side of that resistor, we have created a third branch in our parallel circuit. Okay, so my question is, what is the value of R3? There must be, absolutely. This is the load, this is the resistor in this parallel branch. So what must the value of R3 be? Going back to that original statement, when we add our meter to a circuit to take measurements, it's important that the circuit doesn't change, right? So RT, okay, R1 is going to be whatever R1 is, and R2 is going to be whatever R2 is. They're not going to change no matter what we do. The question is, what must R3 be in order for RT to remain constant? Ooh. Inverse of RT equals inverse of R1 plus the inverse of R2. There was the original circuit. And now plus the inverse of R3. Okay, well the inverse of R3 has to equal 0. So that R1 plus R2 plus 0 equals RT. How do we make this equal 0? What is the resistance? What is the internal resistance of our voltmeter? And I've run out of room, but I need to put an infinite sign right there. So R3 must be infinite resistance, infinitely large, a great big huge number, so that 1 over that great big huge number is equal to 0 and RT remains constant. Okay, so that's really important. We don't want any current because also we want IT to remain the same. So there's current flowing through there and there's current flowing through there, and we want to make sure that there is no current flowing through there, because if there is, then we increase the value of IT. So it's important that that doesn't happen. So there's no current there. Okay, and the reason there's no current there is because that's an infinitely large resistance. It's like an open switch. Okay, so that's measuring voltage. Now here's the trick. Now we want to measure current. Okay, now I'm going to change my circuit a little bit, because if I try to measure current, I'm going to create a combination circuit, and then we're going to have all kinds of trouble. So let's back it up a step and let's make it just a simple circuit like this. And then we're going to add our ammeter. Now, if any of you have had a chance to work, and I wish I had one, I can't seem to find it today, a multimeter that does not have a clamp on it, okay, what you'll notice is you have different spots to plug in your leads. And when you want to measure current, you have to actually move one of your leads into a different plug in your meter. So it's a different circuit in the meter when you're measuring current. Very good reason for that, which we're going to discover right now. How do I measure current? Well, in a circuit, and I could have many series resistors connected here, but the current would be constant all the way through, right? And so to measure current, we simply want to get that current, whatever it is, flowing through our ammeter. So we have to actually break open the circuit, open it up, so turn the power off, open it up, add your ammeter in series in this circuit, and then turn it back on, and the current flowing through the circuit is now going to flow through your ammeter as well. Okay? But now, let me ask you the question. R1, this equation I better get rid of. Okay, RT equals R1. There's the equation originally, before we added our ammeter. Now let's place our ammeter in here. This is now R2. Okay, so R1 plus R2 is now how we find the value of RT. Now once again, it's absolutely vital that we not change the circuit when we add our meter to it to take a measurement. And so we still need R1 to equal RT, which means R2 must equal 0 ohms. Okay, so that we don't change RT, so that that value of I, which we want to measure, is still the same number. We didn't change that because we added our meter to the circuit. Okay, so this is the reason why we have to move the lead in the meter from one circuit to another. It's a completely different circuit. The internal resistance of our voltmeter is off the charts huge. The internal resistance of our ammeter is as small as humanly possible. Okay, now here's the reason why it's important for us to know this. that's interesting and all that. But here's the reason this becomes a really big deal. Because this happens very often with students, and actually with older electricians who aren't students. But if you're asked to take some measurements in a circuit and you're not paying attention, you get confused, or you don't remember what you're supposed to be doing, this happens quite a lot. I'm going to take my multimeter and I'm going to measure with my leads from one side of that resistor to the other, but oops, I've got it set and plugged in to my ammeter circuit to measure current. What have I just done? What is the resistive value of what is the internal resistance of the ammeter? We've just created a parallel branch in our circuit with zero resistance, otherwise known as a short circuit. How much current is going to flow through that ammeter? How much current can our power supply push? Okay, 10,000 amps? I don't know. Okay, more than that ammeter is ready to handle. So best case scenario is you blow a fuse. Okay, either the fuse that's right here, okay, or more likely actually, within the internal circuitry of your multimeter, you will have fuses. Okay, the little glass fuses in your ammeter. Okay, specifically for your ammeter circuit, because you try to measure current that's greater than the meter is capable of handling, or you make this mistake. Okay, that's the best case scenario, is that you blow the fuse. Okay, it's not at all unlikely that you might actually burn up the circuitry of your multimeter. Okay, so there's a problem. Now, here's another mistake you might make, but it's not nearly as devastating. If you make the mistake of placing your voltmeter in there, okay, remember the resistance here is infinitely large. That's just like an open switch. So you don't damage anything, you don't have to go replace any fuses, but you've definitely changed your circuit and now you're not taking any useful measurements. Okay, so the internal resistance of your voltmeter, off the charts huge. The internal resistance of your ammeter, virtually non-existent, which is why when you're using your leads to place your ammeter in the circuit as opposed to clamping on, okay, everybody now is lazy and it's easy because you can cheat, but probably underlines the importance of this understanding, because if you ever find yourself in a situation where you have to measure current using an old style ammeter that doesn't clamp on, you have to actually place it in the circuit, make sure you put it here and you don't do this.